Hello, everybody. Welcome to one of the most exciting sessions of NestGen 23. So, with an emerging focus on drone autonomy, this session will give you a deep learning on how to conduct pilotless BVLOS flights while keeping safety in mind. You'll get an understanding as to how to detect cooperative and non-cooperative aircrafts and why they're important for BVLOS operations. Right. So, flying a drone beyond visual line of sight is becoming increasingly popular due to the numerous benefits it offers. However, to ensure that operations go smoothly, a safe airspace is essential. This helps mitigate the risks associated with BVLOS operations, such as mid-air collisions or even people and property on ground. If you've noticed, majority of today's flights require a visual observer to monitor the skies for potential obstacles that the drone may encounter. In turn, the observer has to notify the pilot immediately. Thus, any lapse in communication is very dangerous. But as drone operations expand, relying solely on human intervention becomes increasingly challenging. So worry not. To show you the way forward, we have Dan with us today, Director and Global Sales at Customer Success at Iris Automation, joining us today. Iris Automation specializes in monitoring the airspace for large-scale drone operations, making sure no two aircrafts ever collide mid-air. Dan has aided their vision to incorporate the detect and avoid DAA systems into all aircrafts in the coming future. With a strong background in SaaS, edge computing, Internet IoT, and regulatory compliance, Dan has worked with several Fortune 500 companies. He has helped contract custom SaaS integrations and navigate complex regulatory environments. He has a long history of working in technology, including time at the Oracle and Verisk Analytics. Dan holds an undergrad degree from Connecticut College with honors and has even taken additional courses at the Tufts. What's more, in his free time, Dan enjoys playing the guitar and entertains his wife and son. So before we jump into Dan's session, I need to share a few housekeeping rules. So please type your questions in the Q&A tab of the session and it'll be answered after the presentation. The session is going to be recorded and will be published soon. Also, we have an Irish automation booth in the expo session, so please make sure you visit it. And finally, please remember to capture your favorite moments from the session and share it on Twitter by using the hashtag NestGen. A few lucky people who share it might have a surprise in store. And also, last but not the least, I would like to thank our sponsors, DJI Enterprise, who's our title sponsor, and Volatus Airspace, who's our platinum sponsor. Right, so with that, over to you, Dan.
Great. Well, thanks so much, Natasha. Let me just get my screen shared here, and we'll bring up the presentation, and then we'll jump right into it.
Yep.
All right. Can you see my screen?
Yes, we can.
Excellent. All right. Well, thank you again, Natasha, and thank you especially to the entire Flightbase team for hosting us. I'm sure some of the folks that are kind of trickling in at this point got to see Iris CEO John Damish on the regulatory panel discussion earlier today. So we're thrilled that Natasha, you and everybody else at Flightbase could host myself for this discussion and John for the earlier discussion. And thank you to everybody that's joining right now. So really thrilled to be talking with you. Detect and avoid technology is kind of one of these discussions that just, God, garners so many questions, and it seems like it's such a hot button topic for a lot of people. So I'm excited to talk to everybody about it, and hopefully kind of give you guys some best practices for incorporating DAA tech into BVLOS waivers. So a little bit about Iris Automation, and I'm going to also cover a couple biases that I think might be worth kind of discussing up front, but a little bit about Iris Automation. We are a detect and avoid manufacturer. We're based in Reno, Nevada, about 35 employees currently, and we have some really great key investors. And we've been in the space for a while now, going on about, we're coming up on 8 years, so founded in 2015. And our customers using the system, using various iterations of our system, have been able to achieve 40 BVLOS approvals globally. We also sit on a number of different standards bodies, RTCA, ASTM, EuroK. We are also deeply involved in JARIS, and of course have participated in different FAA and Transport Canada programs such as Beyond the BVLOS ARC, as well as some testing programs up in Canada with the National Resource Research It's going to be a long presentation, guys. The National Research Council, which is basically Canada's version of NASA. So that's a little bit about us. So those biases that I talked about. Well, first of all, you know, if you couldn't tell from my accent, I am an American. And, you know, most of our customer base is based here in the United States. So this presentation may be a little bit US centric. It is US centric. Let's call a spade here. So I'm going to do my best to try to give best practices that would be relevant to anybody in any jurisdiction that's looking for BVLOS approvals or incorporating detect and avoid into their ConOp. But yeah, I am going to kind of fall back on US regulations just because that's kind of the space that I exist in the most. Right. The other bias that I want to call out, well, I mean, I'm the sales guy, right? Like it's my job to sell this product, and I've been at Iris for about 3 years now. So that being said, I don't want this to be a sales presentation. I'm going to work really, really hard not to make this a sales presentation. I'm going to be talking about different types of detect and avoid technology, how it's relevant to BVLOS operations, the pros and cons of this, and none of this is supposed to be a victory lap for Iris Automation. It's about making sure that you all have the power and are educated about the different types of systems that are out there, the different types of things that you need to consider when utilizing DAA as part of the BVLOS application. So I'm going to do my best to make sure that I don't overly kind of try to sell you guys on Iris stuff. I hope that after this conversation you talk to me because you're interested, but this is not going to be a sales pitch, and I'm going to work hard not to make it such. Okay? Sound good, everybody? All right. Let's jump in a little bit. So we're going to cover a few different topics here. So I'm going to start by kind of expressing the problem of see and avoid. So why this is a difficult thing to solve, where it's coming from in the regulations, at least the US regulations, and before kind of getting into a description of what detect and avoid technology is, we'll talk about cooperative detection systems, visual observers, kind of the advantages, disadvantages of those before getting into non-cooperative detect and avoid technology types, and finally getting into where these all fit in within the regulatory approval process. And we'll have some Q&A time at the end. Okay. So the see and avoid requirements. So yeah, I said this is going to be a little bit US centric. So of course I'm going to quote US regulations here. So the see and avoid requirements, and every country has variations of this, various wording, but it all kind of comes back to the same thing. 14 CFR 91.113 subsection B in the United States makes it really clear that people that are operating an aircraft need to be able to see and avoid other aircraft. Really cut and dry. Part 107.31 subsection A, again from 14 CFR, kind of makes this a little bit clearer. And Part 107 deals more with commercial drone operations, but the idea here is that you have to be able to see the unmanned aircraft, and because you have to observe the airspace for other air traffic and hazards and determine that the unmanned aircraft that you are flying does not endanger the life and property of another. Okay, so the see and avoid requirements are really, really clear. It is incumbent on us as drone operators to make sure that we are avoiding other aircraft. This is not easy to do. Here's a picture from one of our onboard systems. And if you're looking at this, there is a kind of helpful little bounding box down here in the corner that shows the detected intruder. But you can imagine that if you're flying, especially if you have like a handheld system with a really small, like cell phone sized, display, it could be really, really difficult to pick out. Even if you're looking, our cameras are monochromatic, but even if you're looking at a color camera or colored image, that it could be really, really difficult to pick out among all the other noise in the image, a potential intruder. And that's really the crux of the issue here. How do we maintain, make sure that we are staying compliant with those see and avoid requirements? And depending on what we're looking at, it can be really, really hard to pick out these different types of objects. So, if anybody has a guess, feel free to drop in the chat before I kind of reveal what exactly this object is. But this is a non-cooperative aircraft. Specifically, it is a paraglider. So very small, no radio, no ADS-B transponder. There's very low to zero engine noise. It's a little hard to tell if this person does have an engine on the back of that parachute, but of course this is flying at low altitude. And these are the types of aircraft that become the most tricky to find, and they are the types of aircraft that really worry global regulators when we start talking about long-range BVLOS operations or fully autonomous BVLOS operations, because they are the most difficult ones to spot. So this is where detect and avoid technology comes into play. And so we'll start by kind of defining what detect and avoid technology is. So for the purposes of this conversation, because there are lots of different types of different definitions and different terms, detect and avoid, sense and avoid, obstacle avoidance. But for the purposes of this presentation here, we're going to talk about detect and avoid as a system that has the capability to detect both cooperative and non-cooperative aircraft. And that aircraft is going to that aircraft part is going to become important a little bit later on when we start to talking about detect and avoid types. But the whole idea here is that we really want this technological solution that can spot these different types of aircraft, be able to report them back, and with enough time to maintain what's called well clear and avoid collisions. There are multiple different types of detect and avoid that are out there, and they all have their benefits and drawbacks. And as I go through the different types of detect and avoid over the course of this presentation, I want everybody to realize, for just really briefly, none of these are a silver bullet. They all layer into your overall strategic mitigation. Right? Like, so we look at detect and avoid as really what's called a tactical mitigation. In some ways, you could think about it in terms of like a, I don't know, a proximity sensor, that something has gotten close enough to the aircraft or has encroached on the operational area where some type of risk mitigation or deconfliction needs to happen, usually an avoidance maneuver, right? But this is just one overall piece, and just having a detect and avoid system integrated into your CONOP is not going to be a guarantee of BVLOS approval. There could be other pieces of the CONOP that could be limiting or disqualifying for BVLOS operations. So really something to bear in mind is that regulators really try to look at your operation holistically. They want to make sure that systems are integrated properly, that they're functioning the way that they're described in whatever application you have, and that, you know, that basically the overall safety picture is good. And detect and avoid can be a critical aspect of that and can be enabling for more types of advanced BVLOS operations, which we'll talk about in future slides. So the question is, can I just use visual observers? Well, Natasha already kind of touched on this in some of the introductions. Yeah, you could, but visual observers have some really obvious drawbacks, right? So I like this study from Vance et al. I believe that this is, he's from Oklahoma State University. This is a little bit old, published in 2017 or so, but there are a number of different studies out there that talk about the efficacy of visual observers. And, you know, quite frankly, visual observers are relatively limited. You know, we humans have our imperfections, right? Some more than others, right here. You know, when we talk about visual observers, basically this study came to an interesting conclusion, which was that visual observers were very, very good at picking out or recognizing that there was an intruder aircraft in the area. But where they really struggled was trying to determine the distance separation between that aircraft and the UAV. So in other words, it became really, really hard for them to understand if an intruder aircraft really represented a threat and how much time that existed to deconflict the situation, which becomes really problematic. Right? Now, this study was relatively small. There was about, I think, 30 intercepts total, and so and a relatively small number of visual observers. So I think the people in this, I think it's probably safe to say, and I'm extrapolating a little bit, but the people in this study were well motivated to overperform, right? But humans, you know, generally speaking, we're not perfect animals. Sometimes we're not standing in the right spot. We can only see so much of the sky at once. I wear contact lenses and I have terrible eyesight without them. You know, and we're going to perform in varied states based off of, you know, whether we're tired, distracted, stressed out, if we're ill. And of course, you know, it's difficult to scale. you have like a 75-kilometer long pipeline that you're trying to inspect, then placing a visual observer, every 3 kilometers or so becomes pretty burdensome pretty quickly. So it's not really a good model to work with, especially when there are technological solutions that can see much more of the sky much more quickly, have predictable performance, known margins of error that can be accounted for, that can accurately show where an intruder is, where it's heading, and where it's been. There's much more scalability there overall. One other thing to consider too that's not caught on this slide is, we did a deployment of one of our ground-based systems on top of a water tower in Texas. I don't know how many of you folks are from North America or familiar with the weather in Texas, but in the summer, it gets well over 30 degrees centigrade, well over 100 degrees Fahrenheit. And, on top of a big metal structure that absorbs a lot of heat, you can imagine it gets really, really hot up there. And so trying to stick a visual observer in a location like that for 8 hours probably would end really poorly. And you can imagine the inverse too, if you're doing operations in a very, very cold environment. So weather could absolutely impact human performance and make it really dangerous potentially to have visual observers in certain locations to support the operation. So trying to find a technological solution is definitely going to be helpful. So let's just step back and let's talk about cooperative systems really quickly. So cooperative systems are great, and if you have cooperative systems into your ConOp, then that is going to be a feather in your cap. And I don't think anybody would say that having ADSB receiver being able to display cooperative traffic is going to hurt the safety case of your overall operation. But the part of the problem that we're seeing, and we'll talk about kind of the current regulatory state in a little bit and kind of where cooperative detection systems fit more perfectly. But if we're looking at, doing operations that, fly relatively high, flying over long distances, then cooperative detection is not going to be fully comprehensive. And that's one of the challenges of it. Now, it's really hard to get good data on the amount of non-cooperative flights in any one airspace at any one time. It's really variable per country depending on different ADSB mandates, and nobody really has a good comprehensive spot. I did find this one study, which was published by a NASA scientist, that calculated it's about 15% of flights in airspaces in the US that are non-cooperative, but it really varies by country, and even within the United States, which is a huge country, it can vary wildly depending on what part of the country you're in. And I'm sure that there are places in the United States where non-cooperative traffic is closer to 50%, particularly in rural locations where it might be old crop dusters that don't have the electrical systems on board to support ADSB systems. So you can start to see here where the real need for detect and avoid technology for non-cooperative detection really lies. Let's also talk about where these non-cooperative aircraft are flying. Well, primarily visual flight rules, right? One of the questions that I get asked a lot about is weather and what's the impact of weather on our detect and avoid system. And in some ways, weather's a bit of a red herring, right? Let's call a spade here. That if you have a vision-based detect and avoid system, which we do, that it's not perfectly analogous to the human eye, but if there is decreased visibility, it is going to impact the performance of our system. And the other types of detect and avoid systems that we'll talk about in a little bit also are impacted in their own unique ways by weather as well. But once we kind of cross that threshold into IFR, where people are required to be in contact with air traffic control or be on radar with air traffic control, or at least communicative, we start seeing these non-cooperative traffic really drop off. It's also just not safe to fly with an older aircraft that doesn't have the electrical systems to support the instruments needed to do IFR effectively, right? So we're less worried about non-cooperative traffic and poor weather conditions, but this traffic does tend to fly at lower altitudes, definitely in Class G unrestricted airspace, but really they could also be elsewhere because equipment fails sometimes, right? And you could have non-cooperative traffic within restricted airspace or an ADSB mandated zone, either because somebody just forgot to flip on the transponder or because the transponder failed. So mistakes happen, systems fail. It's pretty rare, but it could occur. Right. So these are the types of aircraft we're worried about. And now let's get into the systems that are designed to detect them. Okay, so we're going to focus on three primary types of detect and avoid for the purposes of the rest of this discussion. So I'll talk a little bit, I'll talk about optical, I'll talk about acoustic, and I'll talk about radar. Some systems that I'm not really going to discuss here are LiDAR, RGB, which is another type of vision technology, or ultrasound. And the reason why I'm not really going to talk about those is because, when we're talking about aircraft detection, we really need to be talking about long detection ranges, right? So, if we think about, some of the most powerful LiDAR systems that are out there right now that are able to go in small UAS, they still have limited range. They can't really see far enough out to deconflict the airspace in an effective way. Now, LiDAR is advancing really rapidly, and we may see that change in the next 5 to 10 years. But, certainly when it comes to RGB or ultrasound, we're just not getting those ranges. Those are going to be really great systems for static obstacle avoidance and, fit under the broader banner of maybe sense and avoid. But for our purposes, we're going to really talk about these three different DAA types, because these are the ones that are going to be able to get you the detection ranges that you really need to be able to safely deconflict. Right. So let's talk about the different deployment types too. So there are different ways that we can think about this. Ground-based deployments, onboard, detect and avoid. And when you're thinking about what type of system works best for your ConOp, well, you got to think about which deployment method works. So this is a drone in a box conference, right? So ground-based DAA is basically where I think most people are going to be interested. And the reasons why are really simple. It preserves swap, right? There's no there doesn't need to be an integration into the flight control system. You just need some type of visualization of the airspace. But there are some drawbacks to that, right? Like, so the advantage of drone in a box is that you can set up a system, kind of set it and forget it. It can be in an austere location, could be completely off grid, and then you're going to have your repeated operations, and you can sanitize that bubble of airspace, which is great. But if you're starting to do something like pipeline inspections and you need to fly 75 kilometers, then you're going to have the same scalability issues that you would have with visual observers, which is just, how much infrastructure do you need to be able to port out to be able to support these systems. So something like when we're talking like there are some longer range detection systems that are out there, but even still, you may need multiple systems to be able to support the full length of the operation, in which case it may be better just to take an onboard DAA system and take that little sterilized bubble of airspace with you. Of course, onboard systems have their own disadvantages. Swap, obviously, every system has power draws, some more than others. You have to integrate it into the flight controller. If you're using an open source autopilot, that's great. And that means integration is probably relatively easy, but not every autopilot's open source. Some are proprietary, locked down. Some companies are more willing to work with third parties than others. So there are all sorts of considerations about whether or not you need an onboard or ground-based, but these are kind of the things that you need to kind of be factoring in the back of your head, especially if you're going to be putting this into a waiver, right, or an application for BVLOS. You want to make sure that you have the right technology integrated into your ConOp in the right way. So let's actually talk about the different types of detect and avoid technologies out there, and let's start with radar. And the reason why I want to start with radar is because I think it's pretty much the most well understood to regulators. I mean, this is a technology that's been around in various forms for 85 years plus at this point. It's been around for a while, and its detection ranges can be massive. I've got the detection range of an onboard radar system, and it comes out to right about 3.5 kilometers, 2 miles for those of us those Americans out there that think in freedom units, with a really good field of regard for a single panel. And the real advantage of this, both is range, it's nighttime, it is able to operate in all weather. And with that, because it's really well known, that kind of makes it a little bit easier to work with in some ways than other types of detect and avoid systems. But there are some major cons here. Radar is expensive, especially as you start scaling up the detection ranges, right? It's going to be challenged by particulates in the air. So, we're in Reno, Nevada. We get a lot of the wildfire smoke over from California that blows in. And so in a smoky environment, that's going to affect detection ranges. Low altitude clutter, particularly at detection ranges, is going to impact performance. Curvature of the Earth for the really long detection ranges. You could certainly, and there's a reason why the phrase "flying under the radar" exists, right? And if you have an onboard system, high swap, high power requirements. They're pretty heavy. Public acceptance issues too, right? Like it's kind of a joke, but it's kind of not at the same time. There were people out there during the height of the COVID pandemic that thought that 5G towers could cause COVID, right? Like, and so if you're actively projecting a radar signal out into the world, that can be difficult. Something that John touched on in the earlier presentation too, is just additional regulatory approvals that are required for radar systems, which can be really tough. The FCC here in the United States will require you to get approval from them. So there's an entirely separate approval process that you have to go through just to get to utilize a radar, particularly a ground-based radar. So these are all things that kind of factor in. Radar is really good, though. This isn't just me dunking on radar, but it is really good. It's really well known, and there are certainly folks that have gotten multiple approvals out there using radar systems. But it has its advantages, it has its disadvantages, just like the systems we manufacture, optical systems, right? So our system is passive. It doesn't require any additional approvals because we're not sending signals out into the world. We have really good low altitude detections, really high precision. We're able to say, okay, that object that we're looking at is definitely a plane or definitely a helicopter, or it's a bird, it's a drone, etc. But our detection range isn't quite as good as radar. We have a smaller field of view per camera. We can, certainly mitigate that by using more cameras, but that adds more weight, right? And we talked about some of the challenges already with an optical system. Poor weather, so poor visibility, heavy precipitation is going to impact an optical system. And right now, our optical system is currently daylight only. We're working to fix that, and we're actually hoping by end of year to be nighttime only, and we've seen a tremendous interest from, police departments that operate 24/7. So this has become a really high priority for us, but it is a daylight only system at the moment. So definitely consideration if your operations are 24/7, that, an optical system is going to be challenged by that. And even though we're lighter than a radar system, we still weigh, right? We still draw power. It's not a ton of power. It's not a ton of weight, but it is still weight. And I'll give an example here. So the radar system that I talked about on the last page, I think it's about 2.6 kilograms per panel. I think you need 4 panels for 360-degree field of view. Our system so that's already a lot of weight right there. Our system is 2.4 kilograms for 5 cameras plus the GPU module. So it weighs less, but you still need a pretty hefty bird to be able to carry that. Right? Even though the power draws less, even though it weighs less than a radar, it still weighs quite a bit. And it does take away, and that does come at the expense of potentially other payload you need to carry. So that's why ground-based systems exist, right? Okay, let's talk about acoustic. And then let's get into the rakes part, because I think that's what most people are interested here, right? So again, acoustic passive-based systems. So this I didn't know before doing the research for this presentation, but like ground-based acoustic systems can do detection pretty long range, up to 10 kilometers away, which is pretty incredible, right? Again, all weather capable, certainly functional at night, but there are still some weather challenges, right? Like it's snowing here in Boston where I live right now. So, that's going to mute sounds and probably impact detection ranges. Public acceptance is going to be pretty good, especially thanks to systems like ShotSpotter that are deployed all over the United States. And so people are generally used to this. Pretty low price, low power draw overall, which is great. The real con here is positional accuracy, right? So you may be able to determine that an aircraft is within 10 kilometers of you, but pinpointing that exact location of the aircraft is going to be much more difficult depending on the terrain features, buildings, the noise of the environment. And of course, it's going to be really hard to tell if the aircraft is coming in, going out. And then of course, when we talk about that paraglider that was on, one of the early slides, and that's going to be basically invisible to a system like this. So again, all of these systems have their pros and cons. They've all been used in waivers. They've all been given BVLOS approvals, so they can work. It just comes down to which one is going to work the best for your con-op. And if you can layer these mitigations together, incorporate like an acoustic and an optical and a radar, then that's going to enhance your overall safety profile and help when you go for meetings with the regulator. Okay, so we just did a big technological review, right? Now let's talk about considerations when you start going into BVLOS approvals. The big thing that we at IRIS are hearing right now is that Well, let me take a step back and talk about where the overall regulations are going, at least in terms of the FAA. So in the start of the new year, the FAA has started incorporating something called shielding into their waivers, which basically means if you're within 50 feet of the ground or a structure, then the FAA is going to give you credit for basically saying that that structure or the ground is probably more dangerous to another aircraft than the UAV will ever be, which is a really smart move, right? That makes a lot of sense. And so the FAA has basically said, okay, if you're doing that and you have some type of detection system, could be non-cooperative, could be cooperative, but there needs to be some type of detect and avoid system kind of built into it, then they're going to allow for true BVLOS flights. But that's not a lot of space to work with. 50 feet's really small, and depending on the capabilities of the aircraft, that could actually be potentially dangerous. And we talk with lots of companies that want to fly higher. And in fact, some of the companies that we work with have gotten waivers to fly as high as 1,000 feet AGL, and are gradually going to incorporate that into a BVLOS approval. So for different flights, for different ConOps, that could be fine. In which case, go forth and go do that mission. But that 50 feet could be really restricting and limiting or dangerous for other types of operations. So when you're thinking about incorporating a DAA system, well, the point is to try to use that DAA system to go beyond that 50 feet. And we've seen some precedent with the FAA with customers using our technology to do that. And so basically what it all comes down to is the FAA and other regulators that we talked with, Transport Canada, EASA, et cetera, really want to understand that the system is going to work in a holistic sense, and that you are going to have enough time to be able to execute a maneuver. Okay, so this is a slide that I use in my presentation, in my sales presentations, to talk about, okay, well, where are we going to place ground-based systems to provide enough coverage? Okay, so the basic idea here is you always want to make sure that even if you're in the periphery of your operational area, you always have that time budget. And that's going to be critical. But the other part of this is that the FAA and other regulators need you to prove it. So you can go out and get an approval by just potentially doing math on paper, but it's going to be relatively restricted until you can go out and do some data gathering. So they want to be able to test, do you have the time at the periphery of your operation to be able to execute that avoidance maneuver? What is that avoidance maneuver? Is it just, are you descending into that shielded environment? Are you doing return to home? Is it pilot initiated? Is it system initiated? In other words, fully autonomous. So all of these things need to be proven out and clearly delineated for whatever regulator you want. And depending on which regulator you're working with, the methodology that they follow to assess the operation, that's going to give you the operational area you can work with. And then you need to scale up the number of systems that you use, either it's optical, acoustic, radar, to be able to support that operational environment. But ultimately, the big thing here is that you need to go out and do the testing ahead of time. So it doesn't need to be a ton of data. It could be potentially like a month worth of testing. It's kind of hard to say, but the more engagement you have with your regulator, probably the better. Certainly the folks at the FAA do like to come out and see operations and validate for themselves that everything's working. So it's not a bad idea to invite them out and give them the chance to really see the operation and just how risky the operation really is, which usually isn't very much, right? Like, these are pretty low risk operations, and we all want our operations to be safe. So just kind of those considerations to bear in mind as you start seeking approvals. So, okay, I think we touched on this a little bit. Can you get an approval with the DAA system? Yeah. Can it be true BVLOS? Yeah. And can you escape outside of that shielding? Yeah, we think we can. We're still doing the work with the FAA. Shielding's relatively new, but the signals that we're getting is that yes, you can. You can do this. And really, the time is now to try to strike. The FAA is engaged. Transport Canada is super engaged. God, Transport Canada are wonderful to work with. Definitely the regulatory body that I think we enjoy working with the most because they're so engaged. They ask so many good questions, and they're really willing to work with you. But the FAA engagement has really taken off this year as well. And of course, EASA is putting a new focus on detect and avoid technologies as operators try to get out of segregated airspace. So we're seeing this really good engagement. We're seeing approvals that incorporate true BVLOS, and we're seeing detect and avoid as part of those approvals. So now is a really good time to do that, to start pursuing this, but just bear in mind that you've got to show the system works holistically, that it is safe, and everything works together in the way that you expect it to. Okay. So I dropped a ton of information. So thank you guys for listening in. Really appreciate all of your attentiveness through this. And of course, you can reach out to me after this. I'll be at the Iris booth, and of course, you can have one-on-one. But I think at this point, I think we're going to open it up to questions here. So, Natasha, I guess take it away.
Yes, yes. Thank you, Dan, for sharing these insights. I'm sure it'll benefit the audience for people who are looking for BVLOS waiver success. Thank you so much. Right. So we would now like to open the house for a round of Q&A. Oh wow, you've got so many questions. All right, let's go with the first one. Pankaj asks, is there any limitation on aircraft detection with the ground-based system in cases like swarming?
So I'm not sure exactly what you mean in terms of limitations for swarming. So if you mean that in terms of how many aircraft can be detected at a time, which is what I think you're going with here, at least with our system, we can detect up to 10 aircraft per camera. Our ground system has 6 cameras, so theoretically we could detect 60 intruders simultaneously. So I think that's what you're going for with that question. So in that case, if you do have a swarm, of course, that could mean any number of different drones that could be in the airspace, but we could detect theoretically up to 60 of them simultaneously. And if they're close enough together, we may end up detecting them in bunches as kind of like a unified detection, but we can potentially do that. I can't speak as well to the other types of detection technology that are out there and how well they would be able to handle multiple detections with swarm, but I think that's what you're going for with that question, so I hope that answered it.
Yeah. Thanks, Dan. All right, there's another one. What is the uptime? What happens when there is connectivity loss in the command center?
Yeah, this is a great question, and this kind of goes back to more what the strategic mitigation is. In that case, so if you do have a loss of detect and avoid, you do need to describe in your application to whichever regulator you're working with what the mitigation is in that case. And so if you're able, like, these systems cost, right? Like they can get rather expensive, particularly with like the large ground-based radar systems. We can get hundreds of thousands, if not millions of dollars for some of those massive systems. So, if you're able to incorporate multiple detect and avoid systems so that they're kind of covering and you got some redundancy there, that's great. That's not always possible in every instance. So you do want to make sure that you describe what happens in those instances. So if you do have that loss of connection, does the operation abort? Do you fly back do you return to home within shielding? So those things need to be worked out. And so I would say, talk with whatever regulator, reach out to them and say, hey, this is what I think would be a proper mitigation in my particular con-op to be able to get around this loss of detect and avoid. Is that going to be acceptable to you guys, or do you want to see something else? So work with them. If you're working with an outside consultant, we offer regulatory services. If you're working with us, we'll help advise you on what might be a good strategy in those instances.
Great. Thanks, Anne. So there's another one. Brandon asks, have you made any progress in using the existing onboard sensors on something like an M300 to provide DAA? At over 5 pounds, the modular system can eat up payload limitations pretty quickly on some industry standard drones, and ground-based systems limit BVLOS operational distance.
Yeah, I mean, this is the trade-off, right? When it comes to something like an M300, I mean, so this is one of those, integration issues. So, we've flown on M300s that are adapted with open source autopilots, and so we can absolutely do that. And there are a number of other aircraft that are out there that can support our multi-camera system, which is much, much heavier. We also have a smaller single camera system that comes in at about a pound, 482 grams. So, it all depends on kind of what works for the particular use case. But yeah, this is the trade-off, and this is what's hard about it. And, one of the general challenges that people are facing is that there's no real detect and avoid mandate in the drone space. So a lot of drone companies just have not integrated detect and avoid as part of their manufacturing process. And I don't fault them for that at all, but it is a reality. The number of companies that I can think of off the top of my head that sell, a drone that weighs under 55 pounds, 25 kilograms, that has a detect and avoid pre-integrated are pretty small. I can really think of like 2 off the top of my head. So there really aren't that many. It is a challenge. It is hard, which is why you kind of got to do these trade-offs, right? I don't really have a great answer for this, unfortunately. It all comes down to, discussions with the regulators, how high you need to fly, how much you can take advantage of. It sounds like you might be American or Canadian, but, how much you can take advantage of shielding, how much you can take advantage of infrastructure masking, or, incorporate other types of cooperative detection technologies into the overall CONOP to be able to kind of mitigate the swap implications for an onboard detection system. So yeah, not a great answer, but this is the challenge we're all trying to solve.
All right. So there's another one. How many waivers have been obtained using Cassia G?
Ooh, good question. So Cassia G, in the United States, we received 2 last March, or one in March, one over the summer. We received one up in Canada. And then we actually just had a customer receive an approval just about a week or so ago with Cassia G. Cassia G is a relatively new system. It really got launched as a formal product in May of last year. So we have a bunch of customers that are kind of in the initial R&D process, but we've had approvals in the United States, in Canada. We've had discussions that are ongoing. So we have a customer that is really on the cusp of getting an approval right now. I think we're waiting on signatures, fingers crossed on that one for an FAA approval. And we're working with a couple other customers in Canada for Cassia G as well that are making their way through the SFOC process that are really kind of chugging along really nicely. So it's a handful right now. It's enough to do proof of concept. So the first waiver that we got was with a single system. We did a 2 systems, so creating a corridor between the 2. We got our first commercial approval, which was true BVLOS for a commercial customer doing inspections that just happened about 2 weeks ago. 2 weeks ago. So really just happened. And then we have an approval that's kind of queued up on the public safety side. We got our first SFOC midway through last year up in Canada, and then we've got 2 more queued up, which I think are going the right way based on our discussions with TC. So it's kind of the state of where things are. So we definitely have those approvals. We've definitely shown that we can do it, and customers are starting to really ramp up.
All right, let's just have one more question. Right, so Vaishali asks, how many DAA systems are there?
And what? Okay, that's a very hard question to answer. There aren't that many, is what it comes down to, because there are, we can talk about different types of radar systems. I can think of 3 kind of commercially available, actually 4. 4 radar systems that are currently on the market that would be kind of priced more for commercial sales that are ground-based. They're also onboard versions. In the optical space, there's really not a lot. It's kind of us. There's one other company that also kind of does onboard detect and avoid using optical sensors, but they really kind of gear themselves more towards manned aviation. So we're kind of inhibiting the same space, but not quite. We kind of have our own niches. And then on the acoustic space, there's one really prolific company on the acoustic space, and then there is another company that just developed their own acoustic system for their specifically for their own onboard usage. So there isn't really a lot. There aren't a ton of detect and avoid options out there, and certainly nowhere near as many detect and avoid options as there are different drone manufacturers that are out there. But there is some choice. There are systems available out there to help, and there are a lot more cooperative detection systems, a lot more manufacturers of like Mode S transponders, FLARM, ADSB receivers. So there are a bunch of there are choices out there, but there aren't a whole lot of them, at least not yet. We'll see how the market kind of develops as regulations develop, and we'll see if there ends up being more competition in the space as autonomous drone operations become more prolific globally.
Right. All right. Thank you so much, Dan. This definitely helps us see the path forward to the adoption of BVLOS operations. Would you like to share some closing thoughts?
No, well, thank you so much, and thank you for to everybody that joined and for all the questions. Really, really appreciate it. I'm going to hop over to the Iris booth, so feel free if you have some one-on-one questions to join me there. Otherwise, enjoy the rest of your show, everybody.
Yeah,
Thank you again.
thank you everyone for joining.